Every physicist agrees on one thing: observation changes reality. Watch a particle and it snaps into place. Look away and it dissolves back into pure possibility. Scientists at a California university are now running 5 experiments to find out if our entire universe works the same way. A video game that only renders what you can see, if they are right, nothing around you is real until you look at it. We will walk through the double slit experiment, a destroyed hard drive that rewrites the past, a math proof that says simulations are impossible, and the deepest question physics has ever asked. If this kind of content keeps you up at night, subscribe. Let's begin. A single particle just proved that reality makes no sense. It happened in a lab. Scientists fired electrons one at a time through a barrier with 2 narrow slits cut into it. Simple enough. 1 particle, 2 holes, a screen on the other side to catch where it lands. Logic says the electron goes through 1 slit or the other. It lands in 1 spot. Clean, predictable. That is not what happened. The electrons built up a pattern on the screen that looked like ripples on water. Bright bands and dark bands, perfectly spaced. The kind of pattern you only get when 2 waves crash into each other and either cancel out or double up. The problem is, scientists were firing 1 electron at a time. There was no second electron to interfere with. The electron was interfering with itself. That means each electron passed through both slits at once. Pause on that. A single solid particle, something with real mass, went through 2 separate holes at the exact same moment. That is physically impossible by every rule of the world we live in. A baseball cannot pass through 2 windows simultaneously. A coin cannot land on heads and tails at the same time, but an electron apparently can. Physicists call this a superposition. Before the electron reaches the barrier, it exists in all possible states at once, every possible path, every possible location, all happening together. The electron is not traveling in secret through 1 slit while we are not watching. It is genuinely, mathematically spread across both. And here is where it gets stranger. Scientists wanted to know which slit the electron actually used. So they set up a detector at the barrier, a tiny device that would register the path. The moment they turned it on, the wave pattern on the screen disappeared. The electrons started landing in 2 simple clusters, 1 behind each slit. Normal behavior. The interference was gone. The detector changed the result. The electrons behaved differently depending on whether anyone was watching. When the path was measured, the particle chose a single route. When no one looked, it spread out and interfered with itself. The experiment did not change. The electrons did not change. The only difference was information, whether a record of the path existed. That is not a technical glitch. It has been repeated thousands of times in labs across the world, with electrons, photons, and even molecules the size of small proteins. Every single time, observation collapses the spread into a single outcome. Reality, at its smallest scale, behaves differently when watched. Physicists spent decades trying to explain this away. Maybe the detector was physically disturbing the particle, maybe the equipment was interfering. Every alternative got tested and eliminated. The conclusion kept standing. The act of gathering information about a particle's path destroys the wave pattern. The information itself is what does it. Think about what that implies. The universe appears to produce a definite outcome only when that outcome gets recorded. Before the measurement, every possibility coexists. After the measurement, one reality locks in. The other possibilities do not go somewhere. They simply stop. One physicist compared it to a video game loading a room only when the player walks in. The hallway behind you has no floor, no walls, no ceiling. The game calculates it the moment your camera turns. Save the processing power for what matters. That comparison was meant as a thought experiment. A former NASA scientist decided to take it literally, and the experiments he designed to test it are already running. The double slit result left physicists with a problem they could not ignore. If observation changes particle behavior, then what counts as an observation? A human eye? A camera? A machine that records data but no one ever reads? The answer to that question matters enormously because it determines whether the universe is responding to human consciousness or just to information. Scientists designed a follow-up. They set up the same double-slit experiment, but replaced the human observer with an automatic detector, a machine that recorded which slit each particle passed through, but stored the data without any person reading it. No human involvement at all. The wave pattern still disappeared. The machine's record alone was enough. The moment a device logged the path, the interference vanished. The particles behaved like they knew the information existed, even though nobody was looking at it. Then scientists went further. They ran the experiment with the detector on, let the machine record everything, then they erased the stored data before reading it, deleted the records completely. The wave pattern came back. Once the information stopped existing anywhere, the electrons returned to their spread out, both slits at once behavior. The physical setup never changed. The electrons moved the same way through the same barrier in the same lab. The only thing that changed was whether a record of their path survived. This is the observer effect, and it has a specific scientific meaning. In quantum mechanics, observation does not mean a person looking. It means any interaction that produces information about a particle's state. A photon bouncing off the electron and carrying data away. A detector storing a signal. Anything that leaves a trace of what happened. The universe responds to information, and this raises a question that physicists still argue about today. If the universe only produces a fixed outcome when information is recorded, what is happening before that? Is there a real electron traveling toward the barrier, taking a real path? Or does the electron exist only as a cloud of probability until something forces it to become definite? The mainstream answer is deeply uncomfortable. Before measurement, the electron has no single location, no single path. Every possibility exists simultaneously, each with its own probability. The electron is smeared across space like a sound wave, not pinned down like a bullet. Measurement does not reveal which path it took. Measurement creates the path. Reality is participatory. A physicist named John Wheeler spent his career pushing this idea further than almost anyone. He called it the participatory universe. His argument was that observers are not passive. They are not watching a universe that runs on its own. They are actively participating in producing the outcomes that make up reality. Wheeler designed a thought experiment that became famous. He called it the delayed choice experiment. The idea was stunning. Could an observer make a choice after a particle had already passed through the slits and retroactively change which path it took? The answer, when tested in the real world, appeared to be yes. That result forced physicists to confront something they had avoided for decades. The timeline of cause and effect, the idea that past events are fixed and future choices cannot reach back to alter them, may not apply at the quantum level. A particle's history can be rewritten after the fact. If you want to understand how that is even possible, you need to know about the delayed choice quantum eraser, because that experiment does not just hint at something strange. It appears to reach backward through time and erase what already happened. Most physicists see the observer effect and keep their heads down. Thomas Campbell did not. Campbell spent years working as a physicist for NASA. He studied large-scale systems and complex behaviors, and the whole time, a question sat in the back of his mind. If observation is what makes reality real, and if erasing information can undo what already happened, then what kind of universe produces those rules? His answer shocked the physics community when he published it. Campbell wrote a 3-volume book called My Big Theory of Everything. In it, he argued that the quantum observer effect is not a mystery to be solved. It is a clue pointing toward a specific kind of system that behaves exactly the way quantum mechanics describes, a simulation. Campbell's argument was precise. In a well-designed virtual environment, a program does not render every detail of a room when no one is looking at it. A video game does not calculate the position of every leaf on every tree when the player is 5 miles away. That would waste enormous amounts of processing power. So the system waits. It holds possibilities in a kind of unresolved state. The moment a player's camera points at the tree, the system calculates the position of the leaves and renders them. Campbell said that is exactly what the double-slit experiment shows. The electron exists in an unresolved state, spread across all possibilities, until an observer interacts with it. At that point, Reality calculates a single outcome and locks it in, exactly like a render engine producing a frame. He went further. The erasure result, where deleting the stored data brings back the wave pattern, matched his model perfectly. If the simulation sees that no record of the path exists anywhere in the system, it has no reason to commit to a single outcome. It reverts to an unresolved state, saves the processing power, keeps its options open. Campbell was not writing science fiction. He was building a physics framework, and he wanted it tested. He contacted researchers at California State Polytechnic University. He brought funding from a scientific organization called the Center for the Unification of Science and Consciousness, and he proposed 5 specific experiments, each one designed to probe a different prediction his model made about how a simulated universe would behave. The experiments are running right now. Each one asks a slightly different version of the same core question. Does reality render itself completely and continuously, whether or not anyone is watching? Or does it calculate outcomes only on demand, the way a smart system would if it were managing limited resources? If the universe behaves like the first option, Campbell's model is wrong. Standard quantum mechanics wins. Reality is genuinely strange but fully real. If the universe behaves like the second option, the implications are staggering. Every object around you, every wall, every chair, every body exists as raw probability until something interacts with it. Reality is not a place, it is a process, a calculation running in real time. Campbell spent years waiting for the technology to catch up to his predictions. Now it has. And the experiment that his team considers the most important is not a camera or a slit or a detector. It is 2 USB drives, and one of them needs to be destroyed at exactly the right moment. The lab at California State Polytechnic University does not look like the place where reality goes to get questioned. Ordinary equipment, standard university space, but the 5 experiments running inside it are designed to do something no lab has tried in quite this way before. They aim to test whether the universe renders reality the way a computer renders graphics. Each experiment is a variation of the double slit setup, the same basic structure that produced the original observer effect result. A particle source, a barrier with 2 slits, a detector, a screen, but each version changes one specific variable to test a different prediction. The first experiment is the baseline, standard double slit with a detector watching which slit each particle uses. Result expected, no wave pattern. Confirmed across decades of physics research. This is the foundation everything else builds on. The second experiment removes the human. An automated detector records path information. No person reads it. The question is whether machine-generated records have the same effect as human observation. Based on earlier results, they do. The wave pattern still disappears, but Campbell's team wants clean, controlled data from their own equipment before moving to the more radical tests. The third experiment introduces a delay. The detector records path data, but that data gets held in a temporary file. The particle hits the screen before anyone decides what to do with the file. After the particle lands, a coin flip determines whether the file gets opened or deleted. The result on the screen should already be set. The particle already landed. The question is whether the outcome on the screen changes depending on what happens to the data afterward. This is where things stop feeling like physics and start feeling like something else entirely. The fourth experiment pushes harder. 2 detectors run at once. One watches the particle's path, one records the pattern on the screen. Both save their data independently to separate drives. A random process destroys the path data before either file gets read. If the screen pattern shows interference, it means the universe decided the particle went through both slits after the path information was already gone. The fifth experiment is the one that keeps physicists awake. It is designed to test whether the universe can retroactively reassign a particle's entire history based on what happens to information in the present. If destroying a record of the past changes what the screen shows, then causality, the rule that says past events cannot be altered by future actions, breaks down at the quantum level. Campbell's simulation model predicts that All 5 experiments will show the same pattern. Reality locks in only when information is secured. When information disappears, reality reverts. The universe is not a stage where events happen and get recorded. It is a calculation that produces events only when a record is requested. Standard physics has a different prediction. The outcome locks in at the moment of the event. Later, choices about the data should not matter. One of those predictions is about to be tested with precision that was impossible just a decade ago. And the 5th experiment, the one about destroying records and rewriting history, depends entirely on what happens to a USB drive at exactly the right moment. 2 USB drives sit on a table. One of them holds the path data, the record of which slit each particle passed through. The other holds the screen pattern, the record of where each particle landed. A coin flips, and one drive gets destroyed. This is the center of Thomas Campbell's most ambitious experiment, and it is more unsettling the longer you think about it. Here is the setup in full. A particle source fires electrons one at a time through the double-slit barrier. A detector at the slits records which slit each particle uses. That path information goes to the first USB drive. The pattern that builds up on the screen goes to the second USB drive. Both drives collect data independently. Neither file gets opened. No human looks at any of it during the experiment. After every particle has fired and landed, a random process, a coin flip, or its digital equivalent, selects one drive for deletion. If the flip selects the path drive, that record is wiped completely and irreversibly. The screen data survives untouched. Then, and only then, does a researcher open the screen file and look at the pattern. Campbell's model makes a specific prediction for this moment. If the path data was destroyed before anyone read it, the universe never had a committed record of the particle's path. The simulation, if that is what this is, held the particle in an unresolved state and never had a reason to lock it into a single slit route. So the screen pattern, opened after the deletion, should show the wave pattern, the interference stripes, the sign that the particle went through both slits. If the path data survived and got opened, the screen pattern should show 2 simple clusters, no interference. The particle took a definite path, and the record confirms it. The staggering part is that the screen data was written before the coin flip. The particle's already landed, the pattern is already in the file. A researcher is opening a record of something that already happened. And yet, according to Campbell's model, what the researcher finds depends on a decision made after the fact. This would mean the future can change the past. Physicists call this kind of result retrocausality. The idea that information flowing backward through time, not physically, but in terms of what reality commits to, can alter outcomes that appear to be settled. Most physicists reject this as impossible. Causality is a load-bearing wall of physics. Pull it out, and the whole structure of science trembles. But the quantum eraser experiments that already exist suggest something close to this is real. Deleting which path information after a particle has traveled does appear to change whether the wave pattern shows up. Those results have been replicated. They are published. They are genuinely unexplained by standard physics. Campbell's experiment is a cleaner, more controlled version, designed to close every loophole, designed to produce a result with no ambiguity. If the result matches his prediction, the conclusion is hard to escape. Reality does not write its history until someone reads it. The universe is keeping its books open until the last possible moment. And if that is true, the universe is behaving exactly like a system trying to conserve resources, exactly like a simulation deciding what to render. Before Campbell's USB drive test, another experiment already cracked open this door. The delayed choice quantum eraser is one of the most debated experiments in all of physics. It has been run multiple times in multiple countries, and the result is the same every time. Something appears to happen that should be impossible. Here is how it works. A particle source fires a photon, a single packet of light, toward the double-slit barrier. Instead of a screen on the other side, there is a special crystal. When the photon passes through the crystal, it splits into 2 photons. Scientists call them the signal photon and the idler photon. They are linked. Whatever happens to one affects the other, even at a distance. The signal photon travels toward a screen and lands somewhere. Its landing position gets recorded. The idler photon travels a different path, much longer, toward a second detector far away. Now here is the key. If the idler photon hits a detector that records which slit the original photon came from, the signal photon's pattern shows no interference. 2 clusters, definite path, standard result. But if the idler photon gets routed to a detector that erases its which path information, something strange happens. The signal photon's pattern, already recorded before the idler reached any detector, shows interference stripes. The signal photon landed before the idler photon's fate was decided. The screen recorded the result first. The choice about the idler came second, and yet the screen result matches what the choice demanded. The outcome of the first event appears to depend on a decision made after it already happened. Physicists have spent decades trying to reframe this result to make it feel less impossible. Some argue that we are misreading the statistics. Some say the correlations only appear when you sort the results after the fact, so no real retrocausality exists. Others say the many worlds interpretation absorbs the result cleanly, without any backward time influence. But nobody denies the pattern in the data. When you sort the signal photon hits by what happened to the idler, 2 completely different pictures emerge from the same dataset, one showing interference, one showing 2 clusters. The universe stored both outcomes inside the same experiment and revealed them based on a later decision. That is the part Campbell latched onto. His model says the universe kept the signal photon's outcome unresolved in its records until the idler's fate was determined. Even though the signal photon landed first, the simulation did not finalize the entry. It left the file open. When the idler's information was erased, the simulation wrote the interference result. When the idler's path was recorded, it wrote the cluster result. This is a universe that edits its own history. Think of it like a photo that exists in your camera roll, but has not been fully processed yet. You can still apply a filter. You can still change how it looks. The photo is taken, but the final image is not locked until you export it. Campbell says quantum mechanics is telling us that all of reality works this way. Every event is taken but not yet exported, and somewhere there is a system deciding when to press render. Picture a massive open-world video game, the kind where you can walk for hours in any direction. The game world is supposed to be enormous: mountains, forests, cities, oceans, all of it stretching in every direction. If the game tried to calculate every blade of grass and every shadow in every corner of that world at the same time, the system would crash. No hardware on Earth could handle it. So the programmers built a rule: only render what the player can see. Everything else stays unresolved. The moment the player turns around, the system generates the new scene. The moment they look away, it stops calculating. The player never notices. From inside the game, the world feels completely real, solid, continuous, always there. Thomas Campbell says our universe uses the same rule. His model, which he developed over decades of work in physics, says the universe is an information system. It manages resources, it holds quantum states in superposition, because superposition is computationally cheap. A particle spread across all its possible positions costs almost nothing to maintain. Committing that particle to a single definite location requires a calculation, so the system waits. It calculates only when something forces it to. An observer forces it to. The moment a particle gets detected, the system runs the calculation, produces an outcome, and locks it into the record. Before that moment, the particle is like the grass in the unrendered part of the game, real in the code, unresolved in practice. This is why the double-slit result makes sense inside Campbell's framework. The electron spreads through both slits because the system has not been asked to commit it yet. When the detector registers the path, the system commits, the spread collapses. One slit, one landing spot, one rendered outcome. The energy savings in this model are enormous. Consider that the observable universe contains more atoms than there are grains of sand on every beach on Earth, multiplied by the number of beaches that could fit on Earth again and again. If every atom required constant calculation regardless of observation, The processing cost would be unimaginable. A smart system would never do that. A smart system renders on demand. Campbell also points to the specific texture of quantum randomness. When a particle is measured, the outcome is genuinely unpredictable. Physicists have tested this exhaustively. There is no hidden variable determining the result ahead of time. The universe appears to generate outcomes fresh at the moment of measurement. A system generating outcomes at the moment of query based on probability distributions stored in advance is functionally identical to what a simulation would do. Not every physicist accepts this framing. Most resist it strongly. The simulation hypothesis sits outside what most researchers consider testable physics. Critics argue that calling the universe a simulation adds nothing to our understanding unless you can specify what the simulation runs on. Campbell agrees. That is exactly why he built his experiments, to find the signature of a render engine inside real quantum data. And the signature he is looking for is specific. A universe that renders on demand would show different statistical patterns depending on whether information is preserved or erased. His experiments are designed to measure that difference precisely. The USB drive test is the cleanest version. But to understand why it matters so much, you need to understand what observation really means at the level of quantum physics. Because the answer involves consciousness. And that is where physicists start to seriously disagree. A camera sees the electron? Does that count? This question has caused more arguments in physics than almost any other, because the answer determines whether the universe responds to physical information or to something deeper, something like awareness. The standard interpretation of quantum mechanics says a measurement is any physical interaction that transfers information. A photon bouncing off an electron counts. A detector registering a signal counts. Consciousness is not required. The universe does not need a mind to collapse a wave function. It needs an interaction that leaves a trace. This version is clean and comfortable. It keeps physics out of the mind-body problem. Consciousness is just a byproduct of brain chemistry, not a special force that shapes reality. But the math keeps causing trouble. The wave function, the mathematical object that describes all possible states of a particle, evolves continuously according to a rule called the Schrödinger equation. That equation says the wave function never collapses on its own. It just keeps spreading, incorporating more and more of the environment into a giant superposition. The detector that measures the electron becomes part of the spread. The lab becomes part of it. The scientist reading the data becomes part of it. If you follow the math strictly, collapse never actually happens. Everything just becomes one enormous superposition of every possible outcome, all existing simultaneously. There is no moment where reality commits to a single result. And yet, when a scientist reads the data, they see one result, one definite number, one outcome. The math says all outcomes should still be alive. The experience says only one survived. Something is cutting that spread short. The question is what? John von Neumann, one of the most rigorous mathematical physicists in history, followed the equations carefully and concluded that the chain of superposition only stops when it reaches a conscious observer. He argued that consciousness is the one thing in the chain that is not made of more quantum parts. Everything else, the particle, the detector, the amplifier, the display, all of it can be absorbed into the growing superposition. But awareness, the actual experience of seeing a result, seems to sit outside the physical chain. Most modern physicists reject this interpretation. They call it unnecessary. They say decoherence, the way quantum systems lose their spread by interacting with the environment, is enough to explain why we always see single outcomes without needing to invoke consciousness. Campbell sits between these camps in an unusual way. His simulation model does not require human consciousness specifically. It requires a conscious agent interacting with the system in a way that produces a record inside the simulation's memory. The simulation checks its own records. If a record exists, it renders an outcome. If no record exists, it holds the state open. This means a camera does count. A machine counts. Any device that writes to the simulation's memory counts. Awareness matters because awareness is what causes agents to create records. But the trigger is the record itself, not the mind. The prediction this creates is testable. The USB drive experiment is designed to separate record creation from human perception. If destroying the drive changes the outcome, Campbell's model survives. If it does not, something else is going on. But there is one thought experiment that has haunted physicists for almost a century on this exact question. A cat, a box, a poison vial, and a rule that says the cat must be alive and dead at the same time. Erwin Schrödinger was annoyed. It was 1935, and quantum mechanics had just been formalized into a working mathematical theory. The equations were precise, the predictions were extraordinary. But the interpretation made Schrödinger furious. He was one of the physicists who built the theory, and he believed his colleagues were drawing the wrong conclusions from it. So he built a trap. Imagine a sealed box. Inside the box is a cat, a small flask of poison, and a device linked to a single radioactive atom. The atom has a 50% chance of decaying within 1 hour. If it decays, the device triggers, the flask breaks, and the cat dies. If it does not decay, the flask stays sealed, and the cat lives. The rules of quantum mechanics say that before you measure the atom, it exists in a superposition of both decayed and not decayed states. All its possible outcomes exist simultaneously. The atom has not chosen a state. It is both at once. Here is Schrödinger's trap. If the atom is in both states, and the atom is linked to the flask, and the flask is linked to the cat, then the cat must also be in a superposition, alive and dead. At the same time, inside the sealed box, Schrödinger did not believe this was actually happening. He built the scenario to show how absurd it is to apply quantum rules to the everyday world. He expected his colleagues to be embarrassed and fix the theory. They were not embarrassed. They got fascinated, because the thought experiment revealed a genuine problem. Something must happen when a quantum system interacts with a large-scale everyday object. At some point, superposition breaks down. You never open a box and find a half-alive cat. Reality produces one outcome every time. But the equations of quantum mechanics do not include a rule that says when this happens. The math just keeps spreading the superposition to everything the quantum system touches. The atom, the device, the flask, the cat, and then the scientist opening the box, all of it becomes one giant superposition according to a strict reading of the equations. Where does the collapse actually happen? Physicists have wrestled with this for nearly a century. Some say collapse happens continuously as systems interact with their environment. Some say it happens when a conscious observer enters the chain. Some say it never actually happens at all, and every possible outcome goes on existing in a separate branch of reality. Schrödinger's cat is still alive and dead, depending on which interpretation you pick, and Campbell's simulation model has its own answer. The cat's fate is unresolved inside the simulation's memory until something creates a record. Open the box, and the simulation writes one outcome to its files. The superposition is a placeholder, a held state, an unrendered room waiting for a player to walk in. What this reveals is that the collapse problem is not just philosophy. It points at something fundamental about how reality produces definite outcomes from clouds of probability. The technical name for that process is wave function collapse, and understanding it requires going one level deeper into what a quantum superposition actually is. Because a particle in superposition is doing something stranger than most people realize. Before a particle is measured, it does not have a location. This is the part people resist. The natural assumption is that the particle has a definite position. We just do not know what it is. Like a coin flipped under a cup. The coin is either heads or tails. We just cannot see it yet. The quantum version is different. The coin is genuinely neither heads nor tails. Both outcomes coexist inside one mathematical object, called the wave function. When you lift the cup, one outcome appears. The other one does not go somewhere. It stops being real. The wave function is a map of probabilities. It describes every possible position, every possible state, every possible outcome for the particle, each one weighted by how likely it is to appear. The wave function can stretch across an enormous region of space. A single electron's wave function, under the right conditions, can spread across a region several feet wide. The electron is not hiding somewhere in that region. The electron is the wave function. That spread is the electron. When a measurement happens, the spread snaps down to a single point. One location, one outcome. Every other possibility in the wave function vanishes simultaneously, no matter how wide the spread was. This is what physicists call wave function collapse. The speed of this collapse is instantaneous, not fast, instantaneous. The entire spread resolves into one point at the same moment, regardless of how large the wave function was. Einstein hated this. He called it spooky action. If the wave function of a single particle stretched between New York and Los Angeles, and you measured the particle and found it in New York, then the entire Los Angeles end of the wave function would have to know instantly to stop existing. Signals cannot travel that fast. Nothing can travel faster than light, according to relativity. Yet, collapse happens with no delay whatsoever. Physicists handle this by saying the wave function is not a physical thing traveling through space. It is a mathematical description of possibilities. When a measurement happens, the description updates. There is nothing physical traveling from New York to Los Angeles, just a calculation revising itself. Campbell finds this explanation revealing rather than reassuring. A calculation that updates itself the moment information is recorded instantly across any distance behaves exactly like software updating a database. The simulation does not need a signal to travel across space. The wave function is in the code. When a record is written, the code revises globally immediately. The mechanism behind collapse is still unknown. No equation in quantum mechanics describes what happens during the transition from many possibilities to one outcome. The equations tell you the probabilities. They do not tell you the mechanism. The moment of collapse is a black box. That black box is one of the most important unsolved problems in all of physics. Generations of physicists have tried to peer inside it. Some have proposed that collapse is caused by gravity. Some say it is caused by the environment absorbing quantum information. Some say it does not happen at all, and every outcome goes on existing in a separate reality. None of these have been proven. What has been shown in hundreds of controlled experiments is that the collapse happens the moment a record is created. Before the record spread, after the record, single outcome. And two particles, separated by any distance, can share a single wave function. Measure one, and the other collapses instantly. That is called entanglement. And it is even harder to explain away. Take two particles and link them together at the quantum level. Physicists do this routinely in labs. They create two photons from the same source in a way that links their properties. The two particles share a single wave function. They are, in a very real mathematical sense, one system spread across two locations. Now separate them. Send one across the room. Send the other one to the other side of the planet. Or, as has been done experimentally, use one that stays on Earth and one launched into orbit on a satellite. Measure the first particle. Its wave function collapses. It snaps into a definite state. The second particle, the hundreds or thousands of miles away, instantly takes on a corresponding state. Before the measurement, both were in superposition. After measuring the first, both are definite and their states are correlated perfectly, every single time. The correlation is too perfect to be coincidence. The two particles are not secretly synchronized ahead of time, carrying hidden instructions from the moment they were created. Physicists tested this directly. A series of experiments called Bell tests checked whether hidden instructions could explain the correlation. They cannot. The particles are genuinely sharing information at the moment of measurement, and that sharing is instantaneous. In 2017, a team in China ran the most ambitious entanglement test ever. They linked two photons on the ground and fired one of them up to a satellite orbiting over 700 miles above Earth. The satellite measured its photon, the ground station measured the other. The results matched with perfect correlation across the full distance. The communication, if you want to call it that, happened faster than any signal could travel between the two locations. The particles behaved as if the distance between them did not exist. Einstein called this impossible. He believed the universe operated on local rules. Events in one location can only affect another location if something physically traveled between them, and nothing travels faster than light. Entanglement broke his picture. He spent years trying to explain it away. He could not. Today, entanglement is experimentally confirmed. It is real, it is reliable, and it is used in quantum communication systems and early quantum computers. What it means for our understanding of reality is still debated. Campbell's simulation model handles entanglement cleanly. If two particles share a single entry in the simulation's database, then measuring one updates the entry for both simultaneously. There is no signal traveling between them. There is no distance to cross. The database just writes a new value to a shared record. In a simulation, distance is a rendered property. The coordinate system exists for the players inside the game. The database itself has no distance. An update to one row happens everywhere that row is referenced, instantly. This is not the mainstream interpretation of entanglement. Most physicists resist applying simulation language to quantum mechanics. But the behavior of entangled particles, instantaneous correlation across any gap, is exactly what you would expect if space itself is a layer of the rendering, not a fundamental property of the underlying system. A physicist named John Wheeler thought about this carefully. He believed that distance, space, and even time might be emergent properties that arise from something deeper, something he called it from bit, reality built from information. He designed an experiment to test whether the past itself is fixed. John Wheeler was not a fringe thinker. He worked alongside Einstein and Bohr. He coined the term black hole. He contributed foundational work to nuclear physics and quantum mechanics. By the time he proposed his participatory universe, he had earned the right to say something strange. His argument started with a question no one had answered cleanly. What is the universe made of? The obvious answer is matter and energy, particles and forces. Wheeler thought that was one level too shallow. Dig deeper, he said, and what you find is information. He called it from bit. Every particle, every field, every physical event exists because a question was asked and an answer was registered. A measurement happened. A bit of information got written down. The universe, in his view, is not a collection of objects sitting in space. It is a collection of answers to questions. The objects appear when the questions get asked. He designed an experiment to test whether this was literally true. He took the delayed choice setup and pushed it to a cosmic scale. Imagine a quasar, a blazing core of a distant galaxy sitting billions of light years away. Between that quasar and Earth sits a massive galaxy. The galaxy's gravity bends light, acting like a lens. Light from the quasar splits and travels two separate paths around the galaxy before reaching Earth. Both beams arrive at our telescopes. Now, on Earth, a physicist decides how to observe the arriving light. If they set up a detector that determines which path the light took around the galaxy, the light acts like particles, definite paths. If they set up an experiment that allows the two beams to interfere with each other, the light acts like waves. The light left the quasar billions of years ago. It has been traveling ever since. And yet, the physicist's choice of detection method, made in the present, determines which behavior the light shows from its entire journey. The past of the photon is not fixed until the present observation locks it in. Wheeler called this the participatory universe because the observer is not passively watching a history that already happened. The observer is reaching back across billions of years and deciding what kind of history the photon had. The photon's journey exists as pure possibility until the measurement happens. This was tested at a modest scale in a 2007 experiment. Scientists confirmed that a photon's behavior over a prior path changes based on a present choice. The result held up. Wheeler spent his final years arguing that the universe is fundamentally self-referential. It creates observers through evolution. Those observers participate in collapsing wave functions. Those collapses produce the definite reality that allows stars, planets, life, and observers to exist. The universe, in a sense, brings itself into existence by arranging for observers to complete its own wave functions. Campbell absorbed this framework and pushed it into simulation language. The participatory universe is a universe that waits for users to generate outputs before writing those outputs to permanent storage. Wheeler and Campbell reach similar conclusions from different directions. Reality is built by observation, not revealed by it. The next question is how small that building process goes, how fine-grained is the grid, and if reality has a grid at all, its smallest unit has already been measured. Space has a bottom. Physicists worked this out through decades of calculations combining quantum mechanics and gravity. Below a certain scale, the concepts of distance and position stop making sense. Space itself becomes undefined. You cannot place a ruler smaller than this limit and get a meaningful answer. That limit has a name, the Planck length. It is the smallest distance that has any physical meaning according to current physics. To picture how small it is, a hydrogen atom is already too small to see under a normal microscope. The Planck length is about 10 million times smaller than a hydrogen atom. It is so far below the reach of any instrument humans have ever built that we cannot measure it directly. We calculated it from the fundamental constants of nature, and it has a suspicious property. The Planck length is a fixed, discrete unit. Space does not appear to be infinitely divisible. You cannot keep slicing it in half forever. Below the Planck length, physics breaks. The equations produce infinities and nonsense. The structure of space seems to have a granularity, a minimum resolution. In a simulated universe, this is exactly what you would expect. Every simulation has a pixel size, a smallest unit below which no detail exists. Render the room at higher resolution, and you get more pixels per inch. But every rendering system has a limit. Below that limit, there is nothing to zoom into. The image just breaks apart. The Planck length could be the pixel size of our universe. Physicists are careful not to overstate this. The Planck length is a mathematical consequence of combining the constants of gravity and quantum mechanics. It is where our equations stop working, which might mean it is where reality stops having structure, or it might mean our equations are incomplete. The Planck length could be telling us about the universe, or it could be telling us about the limits of our math. But the shape of the problem is compelling. A universe with a minimum unit of space, a universe that behaves differently when observed, a universe whose history is written by measurement. All of it points toward a system that processes information on a grid with finite resolution. The idea that the universe fundamentally processes information has its own name and its own school of researchers. They call it digital physics. And one of the most serious thinkers in that tradition was a physicist who spent decades asking whether every physical law could be rewritten as a computation. His name was John Archibald Wheeler. You already met him, but another physicist took the computational idea further than Wheeler did. That physicist argued that everything in the universe, every particle, every force, every field, is a specific kind of information, and that the physical laws governing them are nothing more than the rules of a program running on a cosmic computer. Edward Fredkin had an unusual career path. He was a computer scientist and physicist who spent decades thinking about what happens when you take computation seriously as a description of physical reality. His core idea was straightforward and radical at the same time. The universe does not just resemble a computer. The universe is a computer, a specific kind of computational process where the state of every point in space at one moment is determined by the states of its neighbors the moment before. He called this a cellular automaton. Picture a grid, like graph paper. Every square on the grid has a simple rule. Look at your neighbors. If a certain number of them are filled, you fill yourself next step. If fewer are filled, you empty yourself. Run the rule for every square simultaneously. Advance one step. Then do it again. These simple grids, following simple rules, produce shockingly complex behaviors, patterns that look alive, structures that replicate, move, and interact. Some grid configurations produce gliders, small patterns that travel across the grid indefinitely. Some produce oscillators that pulse with rhythmic timing. Some produce patterns so complex they have never being fully analyzed. Fredkin proposed that the physical universe works the same way. Every point in space has a state, every state updates based on its neighbors, following precise rules. Those rules are the laws of physics. The output of the computation is everything we see, every particle, every force, every field, every galaxy. This view is called digital physics. It is a minority position in theoretical physics. Most physicists think the universe is analog, meaning physical quantities can take on any value within a continuous range, not just discrete steps on a digital grid. But quantum mechanics complicates this assumption because at the smaller scales, many quantities do appear to come in discrete chunks. Energy comes in packets called quanta, spin comes in fixed values, charge is quantized. The universe, at its smallest observed level, does look more digital than analog. And here is the part that connects directly to Campbell and the simulation hypothesis. If the universe processes information on a grid, then two things follow naturally. First, there is a minimum unit of information, a bit, below which no further detail exists. That matches the Planck length. Second, a system that processes information on a grid can, in principle, be run on another information processing system. A simulation inside a simulation becomes possible the moment you accept that the universe is fundamentally computational. Fredkin was not arguing that someone built our universe as a hobby project. He was making a structural argument. The laws of physics look like the laws of a program. The behavior of reality looks like the output of a computation. Whether there is a programmer behind it is a separate question. But once you accept the computational structure, you open a door that is very hard to close. Because if computation can produce a universe this complex, then any sufficiently advanced civilization inside that universe could, in theory, compute another one. And a philosopher at Oxford named Nick Bostrom did the math on exactly that possibility. Nick Bostrom published his simulation argument in 2003, and it is one of the strangest valid logical structures ever written. He started with three possibilities and showed that at least one of them must be true. First possibility: virtually all civilizations reach a point of technological development and then go extinct or collapse before building powerful enough computers. Second possibility: virtually all advanced civilizations, for some reason, choose not to run simulations of their ancestors or of conscious beings. Third possibility: we are almost certainly living in a computer simulation right now. His argument runs like this: assume civilizations can eventually build computers powerful enough to simulate conscious minds. History shows that computational power grows fast. There is no known physical law preventing a civilization from eventually simulating human-level consciousness in a computer. Now assume such a civilization runs just a few of these ancestor simulations. Maybe they run millions of them, studying history, running experiments. Each simulation contains a world full of simulated minds who believe they are real. For every one real civilization, there could be millions of simulated ones. Count the minds. If simulations run at all, the total number of simulated conscious beings vastly outnumbers the real ones. The ratio could be billions to one or more. If you are a conscious being, simple math says the overwhelming probability is that you are one of the simulated ones. The only escape from this conclusion is to believe that almost all civilizations fail before reaching this level of computing power, or that almost all advanced civilizations freely choose never to run such simulations. Both of those require enormous and unsupported assumptions. Bostrom himself has said he does not know which possibility is true. He has described his position as genuinely uncertain. The argument is about logical structure, not personal belief. The three possibilities cover the space completely. You have to pick at least one. Elon Musk picked the third. He has stated publicly that he believes the odds we are in base reality, the original non-simulated universe, are billions to one against. He has said this multiple times in interviews, and while his opinion is not scientific evidence, his reasoning directly follows Bostrom's structure. Scientists generally keep more distance from the conclusion. The argument is logically valid, but depends on assumptions that are hard to verify. We do not know that consciousness can be simulated. We do not know that physical computation can replicate subjective experience. We do not know the survival rate of advanced civilizations, but the structure of the argument is hard to dismiss, and it raises a question that takes the physics in a completely new direction. If the simulation hypothesis is even plausible, then what would it cost to run it? How much processing power would you need to simulate a universe as complex as ours? The answer to that question is either the strongest argument against the hypothesis or evidence that the universe is being run by something we cannot possibly imagine. Elon Musk made this statement at a technology conference in 2016. The odds that we are in base reality, he said, are 1 in billions. He explained that 40 years ago, video games had 2 rectangles and a dot. Now we have games with millions of players and photorealistic graphics. If you draw a straight line through that improvement and project it forward, the gap between a simulation and physical reality disappears within decades. His conclusion: given enough time, any civilization will eventually build simulations indistinguishable from the real thing, and once that is possible, they will run enormous numbers of them, far more simulated worlds than real ones, so statistically, you are almost certainly in one of the simulated worlds. Musk is not a physicist, but he was following Bostrom's structure, and the response from actual physicists has been more complicated than a simple rejection. Some physicists, including serious researchers at major universities, have said the simulation hypothesis is genuinely worth scientific investigation. Max Tegmark at the Massachusetts Institute of Technology has argued that the universe is mathematics, meaning the universe is not described by math, it is mathematical structure, which already puts it one step closer to being a computation than most people assume. Silas Bean and a team at the University of Washington published a paper in 2012 arguing that if the universe is running on a computational grid, it might leave detectable signatures. Specifically, the grid would impose a maximum energy on particles, called a cutoff, because particles with shorter wavelengths than the grid spacing cannot exist. Cosmic rays, the highest energy particles we detect from space, appear to have such a cutoff. The energy limit exists. Whether it comes from a grid or from something else, no one yet knows. Other physicists push back hard. Sabine Hossenfelder, a prominent theoretical physicist, has written that the simulation hypothesis is pseudoscience dressed in mathematics. Her argument is that proposing an unobservable outside system as an explanation for physics tells us nothing and predicts nothing. This is the core tension. The simulation hypothesis either produces testable predictions, in which case it is science, or it does not, in which case it is philosophy. Campbell believes his experiments produce testable predictions. If the universe renders on demand, the statistical signature of that rendering should appear in quantum data when information is selectively preserved or erased. But there is a harder challenge coming, one that attacks the simulation hypothesis from a direction no one expected, not from physics, from pure mathematics. A group of researchers decided to ask whether a simulation of reality is even mathematically possible. And the answer they arrived at drew on a proof from the 1930s that was written for a completely different purpose. The implications turned out to be devastating for the simulation hypothesis, or at least they should have been. In 1931, a mathematician named Kurt Gödel published a proof that shook the foundations of mathematics itself. His incompleteness theorems showed that any formal system powerful enough to describe basic arithmetic will always contain true statements that the system cannot prove. Every sufficiently complex logical system has gaps, truths it can reach but never verify from inside its own rules. Gödel was not talking about physics, he was talking about the limits of logic. But his proof was so foundational that it showed up decades later in a completely unexpected place. In late 2025, a team of researchers at the University of British Columbia published a paper arguing that Gödel's incompleteness theorems make a simulated universe mathematically impossible. Their argument went like this. A computer simulation runs on algorithms. An algorithm is a set of precise rules that a system follows step by step. Every computation, no matter how complex, is built from these formal rules. That is what makes it computable. You can write the program, you can run it, it produces outputs. But Gödel showed that mathematical truth is broader than what any set of formal rules can capture. There are mathematical facts that exist beyond the reach of any algorithmic system. A simulation running on algorithms cannot access those facts. It is structurally limited by its own rules. Now, here is the critical step. The researchers argued that physical reality appears to use these beyond algorithm mathematical truths. The behavior of quantum systems, the structure of physical constants, the geometry of space-time, these seem to rely on mathematical relationships that no finite algorithm can fully compute. They called this non-algorithmic understanding. The universe appears to operate on mathematical principles that sit outside what any computer program can replicate. If that is true, no simulation could produce a universe like ours. The simulation would always be missing something. The truths it cannot reach would create cracks. Physical laws it cannot fully replicate. Behaviors that would look subtly wrong. This would mean the universe is fundamentally real and fundamentally beyond computation. The reaction from the physics community was divided. Some researchers praised the argument as a serious theoretical constraint. Others pointed out that Gödel's theorems apply to formal systems as understood in mathematics, and whether physical reality is actually a formal system in that sense remains an open question. Campbell's team read the paper. They did not abandon their experiments. Their argument is that Gödel's theorems describe limits of formal proof systems, and a simulation does not necessarily run on a formal proof system. A simulation could run on something more powerful than a standard computer, something that operates beyond the limits Gödel identified. An oracle machine, in theoretical computer science terms, is a hypothetical computing device that can resolve questions that standard algorithms cannot. The debate between the two positions reaches a place where physics and mathematics blur together. Can the universe be computed? If so, by what? If the simulator runs on rules we cannot conceive, Gödel's limits might not apply. And yet the UBC result stands as a serious challenge. The deepest level of mathematics suggests reality cannot be copied by any machine we can define, which raises the strangest question in this whole story. If a simulation is mathematically impossible, why does reality keep behaving like one? The answer might lie in something even more fundamental than computation, something physicists discovered when they looked at what happens to information inside a black hole. Kurt Gödel was 25 years old when he destroyed mathematics. Not literally, the buildings stood, the journals kept publishing, but the dream that mathematicians had carried for decades, the dream of building a complete, perfect, airtight system of logic that could prove every true statement, that dream collapsed when Gödel published his incompleteness theorems in 1931. His proof was almost cruel in its elegance. He showed that inside any logical system powerful enough to do basic arithmetic, you can build a statement that says, in effect, this statement cannot be proven. If the system tries to prove it true, it contradicts itself. If it tries to prove it false, it also contradicts itself. The statement is true, but the system cannot touch it. Every sufficiently powerful logical system contains truths it can never reach from inside its own rules. Mathematicians accepted this. They had to. The proof was airtight. What they did not expect was for this result to show up 90 years later in a physics paper about simulated universes. The researchers at the University of British Columbia started from a specific claim. A computer simulation runs on algorithms. An algorithm is a precise set of steps. Given an input, follow the steps, produce an output. Every modern computer, from the one in your pocket to the most powerful supercomputer on Earth, runs on this structure. Algorithms all the way down. Gödel showed that the set of truths provable by any algorithm is smaller than the set of mathematical truths that actually exist. There is a gap, truths outside the reach of any formal procedure. A simulation, by definition, cannot access those truths. It is trapped inside its own rules, just like the logical systems Gödel analyzed. The UBC team argued that physical reality uses the truths in that gap. Quantum mechanics contains mathematical structures that appear to require what they called non-algorithmic understanding. The behavior of certain quantum systems cannot be fully captured by any computable function. The universe seems to be doing mathematics that no computer program can replicate step by step. If that is accurate, then any simulation of our universe would be missing exactly those behaviors. It could approximate them, it could get close, but it could never fully reproduce the mathematical fabric that makes our physics work. There would always be a gap between the real and the simulated. The UBC paper sent a clear message. The universe might be provably too complex to copy. Campbell's response was measured. He pointed out that Gödel's theorems describe limits of formal mathematical systems as defined in the 1930s. A simulator that runs on something beyond a standard algorithm, a theoretical device that can resolve otherwise undecidable questions, would not be bound by those limits. The question becomes what the simulator runs on, not whether a simulator can exist at all. The debate leaves a genuinely open question at its center. One side says mathematics proves the universe cannot be a simulation. The other side says mathematics only proves that a standard computer cannot simulate it, which leaves the door open for a simulator powerful enough to sit outside Gödel's reach. Both sides are working from solid logic. The disagreement is about what kind of system the simulator would need to be. And if such a system exists, it would need to handle something even harder than simulating particles and forces. It would need to handle randomness. True, unpredictable, bottom-of-reality randomness. Because quantum mechanics says that randomness is built into the universe at the deepest level. And for a simulation, that creates a problem with no clean solution. Every password you have ever created depends on randomness. Every encryption system protecting your messages, every shuffle of a digital deck of cards, every roll of a die in an online game. All of it is generated by algorithms, step-by-step procedures that produce outputs that look random, sequences of numbers with no obvious pattern, long enough to fool almost any test. But they are not actually random. They are deterministic. Given the same starting seed, the algorithm produces the exact same sequence every time. Cryptographers call these pseudo-random number generators. The randomness is fake. It is a very convincing imitation. Quantum mechanics says the universe does something genuinely different. When a particle in superposition gets measured, the outcome is irreducibly random. Physicists have tested this with extraordinary precision. There is no hidden variable, no secret algorithm determining the result ahead of time. The particle has a probability of landing in each possible state, and when it lands, the specific outcome is not determined by anything prior. It just happens. This is called quantum indeterminacy. It is one of the most tested and confirmed results in all of physics. The randomness is real. It goes all the way down. For a simulation, this creates a serious structural problem. A simulation runs on rules, algorithms, computable procedures, but real quantum randomness cannot come from a computable procedure, by definition. A computable procedure always traces back to a starting state and a set of steps. That means any output it produces was, in principle, determined the moment the simulation started. There is no room for genuine unpredictability inside a system running on formal rules. So either the simulation uses pseudo-random numbers and the universe's randomness is fake, or the simulation runs on something more powerful than a standard algorithm, capable of generating true unpredictability. If it uses fake randomness, that has a potential signature. Pseudo-random sequences, no matter how sophisticated, eventually show subtle statistical patterns when analyzed over a long enough stretch. Physicists have tested quantum randomness against every known test for pseudo-randomness. It passes every one. No pattern has ever been found. But that result cuts two ways. Either the randomness is genuinely real, or the simulator is using a pseudo-random generator so sophisticated that no test we can build will ever detect it. From inside the simulation, we might never be able to tell the difference. Campbell's model handles this by stepping outside the frame. He argues the simulation is not running on a computer. As we define computers, the system generating reality operates on principles that include genuine indeterminacy as a native feature. The randomness is real inside the simulation because the system running it is more powerful than any formal algorithm. This keeps his model intact, but it pushes the problem one layer up. What exactly is this system? How does it generate true randomness? And where does it get its rules from? Those questions reach towards something physicists call the fine-tuning problem. Because the rules of our universe are set, values so precise, so perfectly calibrated for complexity and life to exist, that pure chance seems like an absurd explanation. It looks, to many physicists, like someone adjusted the settings. The universe runs on numbers. Physicists call them constants: the strength of gravity, the mass of an electron, the speed of light, the force holding atoms together. These numbers appear in every equation. They are built into the fabric of reality, and as far as we can measure, they are fixed, unchanging, the same everywhere in the observable universe. Here is the problem. If you change any of them, even slightly, the universe falls apart. Make gravity slightly stronger, and stars burn out in thousands of years instead of billions. Life needs time, billions of years of time. A stronger gravitational constant eliminates that window completely. Make the force holding atomic nuclei together slightly weaker, and atoms cannot form. No atoms means no chemistry. No chemistry means no molecules, no cells, no biology, no observers. Make the mass of an electron slightly different, and chemical bonds stop working. The periodic table collapses. Water cannot exist. The specific molecules that carry genetic information cannot form. Physicists have mapped out these sensitivities carefully. The range of values that permit a universe with stars, planets, chemistry, and life is extraordinarily narrow. The values we actually have sit inside that narrow range, with no explanation for why. This is the fine-tuning problem. The universe's constants appear selected, dialed in, adjusted to produce maximum complexity. There are three mainstream responses to this. The first is the multiverse. If an enormous number of universes exist, each with randomly different constants, then some of them will land inside the life-permitting range by chance. We live in one of those because we had to. You cannot observe a universe that cannot support observers. This is called the anthropic principle. The second is that a deeper theory, one we have not found yet, will explain why these constants have to be the values they are. Maybe there is no other way. Maybe the constants are the only ones mathematically consistent with a universe at all. The third is design. Someone set them. Most physicists resist the third option because it is outside the bounds of science. You cannot test for a designer. You cannot make predictions from it. It explains everything by explaining nothing. But the simulation hypothesis transforms design into a testable framework. If the universe is a simulation, the constants are parameters, set by whoever built the simulation, chosen for a purpose, or chosen through trial and error, or copied from a template. The fine-tuning is not mysterious in that case. It is engineering. Campbell argues that a simulation designed to produce complexity, consciousness, and experience would naturally be tuned to support them. A simulation with constants that produce a universe of pure hydrogen gas and nothing else would be useless. A good simulation requires the kind of universe that generates interesting outputs. The fine-tuning problem does not prove the simulation hypothesis, but it does make the hypothesis feel less random. A simulated universe has an obvious reason to be fine-tuned. A spontaneous universe arising from nothing has no obvious reason at all. And if someone fine-tuned our universe, that same someone presumably had neighbors, other civilizations, maybe other simulators, which raises a question that has haunted physicists and astronomers for decades. If intelligent beings can build universes, why have we never found any sign of intelligence beyond our own planet? The Fermi paradox starts with a simple observation. The universe is ancient. Stars have been burning for billions of years. Planets capable of supporting life have existed for nearly as long. The laws of chemistry that produce biology work the same across the entire observable universe. Given enough time, life should arise in many places. A simple probability says we should not be alone. The galaxy should be teeming with civilizations at various stages of development. Some of them should be millions of years ahead of us. In a million years, human technology has gone from sharp rocks to space telescopes. A civilization a million years older would be unimaginably advanced. And yet we hear nothing. No signals, no megastructures visible in our telescopes. No visitors, no evidence of any intelligence beyond Earth, despite decades of searching. The physicist Enrico Fermi asked the obvious question at lunch one day in 1950. If they are out there, where are they? Nobody has answered it cleanly. The simulation hypothesis adds a new layer to this problem. If advanced civilizations eventually build simulations, and if they run large numbers of simulations, then the majority of conscious minds in any given universe would be simulated ones. The simulators would be rare. The simulated would be everywhere. A simulated civilization, by definition, exists inside the simulation. It cannot see outside its own layer. The simulators exist in the layer above, running the program. From inside, there is no signal to detect from them. They are not in the same space. They are not even playing by the same physics. This reframes the Fermi paradox completely. We cannot detect the simulators because they are not in our universe. They are running our universe. Looking for them with a telescope is like a character in a video game trying to detect the player sitting at the keyboard. Some researchers have taken this further. They argue that advanced civilizations do exist in our universe, but that once a civilization reaches a certain level of development, it retreats inward. It builds simulations, it runs them, it studies them, it stops expanding physically through space, because the most interesting territory is computational. A civilization that can build universes has no reason to colonize galaxies. The universes it builds are richer, more controllable, and more varied than anything physical space offers. The galaxy could be full of ancient civilizations that have gone quiet because they went inside. This idea is called the transcension hypothesis, and it is one of several attempts to explain the Fermi paradox through the lens of what sufficiently advanced intelligence actually does with its time and resources. None of this proves we are simulated, but the silence of the universe is consistent with a picture where the entities powerful enough to build simulations are not broadcasting, they are building. And if they built ours, there may be fingerprints left behind, anomalies in the physical data that should not be there. Behaviors in quantum systems that look slightly like artifacts of a rendering process. Campbell calls these glitches. A glitch in a video game has a texture. You fall through a floor that should be solid. A wall disappears and reveals empty geometry behind it. An object clips through another object it should bounce off. The rules of the simulation break down at a specific moment in a specific place and show you the underlying structure that the rendering was supposed to hide. If our universe is a simulation, its glitches would have a different texture. Subtler, harder to recognize as errors rather than features, but they might already be in the data. Physicists have catalogued a set of results from quantum experiments that nobody has fully explained. They call them anomalies or paradoxes. The double slit result is one of them. The quantum eraser result is another. But there are others, less famous and stranger. Quantum tunneling is one. A particle hits a barrier that should be physically impossible to cross, given its energy. Classical physics says it bounces back. Quantum mechanics says it sometimes appears on the other side instantly, as if it passed through the barrier without traveling through it. This is confirmed. It is used in everyday electronics. Tunnel diodes, flash memory, and scanning tunneling microscopes all rely on it. In a simulation, tunneling might be a feature of how the render engine handles boundary conditions. When a particle's wave function overlaps a barrier, the system calculates a probability that the particle renders on the far side. The particle does not physically travel through the barrier. The system just decides to place it there. Quantum Zeno effect is another anomaly. Observe an unstable particle continuously and it stops decaying. Watch it closely enough and it freezes. The act of constant measurement prevents the normal evolution of the quantum state. The particle cannot move toward its next state because measurement keeps snapping it back to a defined position. This makes no physical sense in a material universe. A particle decaying through a random process should not care how often you look at it. Its internal chemistry does not change based on observation. But in a simulation, continuous observation means the render engine is constantly being called. The particle's state is being checked and relocked constantly. The system has no opening to calculate a transition. The Zeno effect, in Campbell's model, is the render engine being given no gap to update the particle's status. Wave function collapse itself could be a glitch, or more precisely, a feature the simulation tries to hide. The instantaneous universal collapse of a spread wave function into a single point is mathematically clean but physically bizarre. Nothing in the material world works this way. Physical signals propagate. Effects spread at the speed of light. Instantaneous global updates are exactly what software does. None of these anomalies prove simulation. Each one has alternative explanations within standard physics, but they share a quality. They all involve reality producing definite outcomes through processes that look more like decisions than mechanisms. The universe chooses. It does not mechanically roll out. The deepest version of this quality shows up in the holographic principle, a result from theoretical physics so strange and so well supported that it suggests the three-dimensional world around you might be encoded on a surface you cannot see, a surface that functions exactly like a hard drive. In the 1990s, theoretical physicists discovered something that should have made headlines in every newspaper on Earth. The amount of information needed to describe everything inside a region of space is not determined by the volume of that region. It is determined by the surface area surrounding it. This is called the holographic principle, and it means that reality, as we experience it in 3 dimensions, might be a projection from a 2-dimensional surface. Picture a snow globe. Everything inside, the little buildings, the fake snow, the water, all of it exists in 3 dimensions. Now imagine that every physical event inside that snow globe is fully encoded on the glass surface surrounding it. Every snowflake's position, every splash of water, every atom of the miniature castle, all of it written in information on the outside of the sphere. The 3-dimensional interior is real, but it is not primary. The primary record is on the surface. Physicists arrived at this from studying black holes. A black hole has a boundary called the event horizon. Information that falls into a black hole should, according to classical physics, be lost forever inside it. But calculations by Stephen Hawking, Jacob Bekenstein, and others showed that the amount of information a black hole can store is proportional to its surface area, not its volume. This was deeply strange. Surface area grows slower than volume. A sphere twice as wide has 4 times the surface area, but 8 times the volume. If a black hole's information capacity were proportional to its volume, bigger black holes could store more information per unit of surface. Instead, the surface sets the limit. This pointed toward a universe where the surface is the fundamental record, and the interior is computed from it. Gerard 't Hooft and Leonard Susskind formalized this into the holographic principle. They argued it applies everywhere, not just inside black holes. The entire observable universe might be described completely by information encoded on a boundary surface roughly 14 billion light-years away. Juan Maldacena proved a mathematical version of this in 1997. He showed that a specific kind of quantum field theory living on a flat boundary surface is exactly equivalent to a theory of gravity living in the higher dimensional space the boundary surrounds. The interior physics and the boundary physics produce identical predictions. They are 2 descriptions of the same thing. This is called the anti-de Sitter space and conformal field theory correspondence. Physicists work with it every day. It is one of the most productive ideas in modern theoretical physics, and its implications for the simulation hypothesis are hard to miss. A universe whose physical content is encoded on a 2-dimensional boundary surface looks structurally like a computer screen. The pixels are on the screen. The three-dimensional game world is generated from them. The surface is primary, the interior is rendered. Campbell reads the holographic principle as a direct confirmation of his model's structure. The simulation stores its information on a boundary. It renders the interior from that stored information whenever observers interact with it. The rendering is real. The interior physics is real, but the underlying record is two-dimensional, encoded on a surface that functions like memory. If the universe stores information on a boundary, like a hard drive, then what happens to that information when space itself breaks down? What happens at the most extreme rendering failure in the known universe? What happens inside a black hole? Stephen Hawking had a problem. He had shown, mathematically, that black holes evaporate. Over enormously long periods of time, black holes slowly leak energy in the form of thermal radiation, Hawking radiation as it is now called. Eventually, a black hole shrinks to nothing and disappears. The problem is, what happens to everything that fell in? Classical physics says information cannot be destroyed. This is a deep conservation law woven into quantum mechanics. Every physical state can, in principle, be traced backward to the states that produced it. The universe keeps a complete record. If you burn a book, the information technically still exists, spread across the smoke and ash and heat, recoverable in theory with enough precision. A black hole that evaporates appeared to break this law. Matter and energy fall in. The black hole radiates thermal energy and shrinks. Thermal radiation carries no specific information about what fell in. It is just heat. When the black hole is gone, the information about everything it ever swallowed seems to have vanished. Hawking called this the information paradox. He spent decades arguing that information could be permanently destroyed inside a black hole. Most physicists disagreed. The argument ran for 30 years. In 2004, Hawking conceded. He announced that he had been wrong. Information was not lost. It escaped through the radiation encoded subtly in the quantum correlations of the emitted particles. The black hole's evaporation carried the full record of everything that ever crossed the event horizon, scrambled beyond any practical recovery, but present in principle. The universe refused to delete its files. This result, combined with the holographic principle, produced a picture with striking implications. A black hole stores information on its event horizon, its boundary surface. As matter falls in, the horizon encodes the information. As the black hole evaporates, the horizon transfers that information into the outgoing radiation. The interior is inaccessible. The boundary is the permanent record. Black holes, in this view, are the universe's most extreme data compression system. They take three-dimensional information and flatten it onto a two-dimensional surface. They store it there for as long as the black hole exists, which can be longer than the current age of the universe for large enough black holes, and then they slowly release it back into the universe. In Campbell's simulation framework, black holes map onto something like an archival process, a region of space-time where the render engine compresses local information into long-term storage. The interior of the black hole is not rendered for any observer, because no observer inside can send information back out. The simulation has no reason to maintain a rendered interior. The boundary holds the data. The rendering happens if and when information returns through the evaporation process, which operates on timescales so long they might as well be permanent from any human perspective. Whether or not you accept the simulation interpretation, the physical result is confirmed. Information is preserved by the universe at every scale, including the most extreme environments that exist. The universe appears to be constitutionally incapable of losing its records. A universe that preserves all records sounds like a universe running on a system that cannot afford to lose data. But even with the holographic principle and information conservation taken together, a core problem in quantum mechanics remains completely unsolved. And it is a problem that physicists have been fighting over for 100 years. The disagreement is about what observation actually does. And the people who disagree are not amateurs. In 1927, physicists gathered in Brussels for a conference that should have settled the interpretation of quantum mechanics. It did not. Niels Bohr argued that quantum mechanics is complete. Particles do not have definite properties before measurement. The wave function is all there is. Asking what a particle is doing before you measure it is a meaningless question. Einstein disagreed. God does not play dice, he said. The universe has definite states whether or not we look at them. Quantum mechanics is incomplete. There are hidden variables we have not found yet that determine the outcomes. Bell proved in 1964 that Einstein was wrong about the hidden variables. The particles are genuinely indefinite before measurement. But Bell's result did not settle what that means. 100 years later, physicists still hold fundamentally different views on the interpretation of quantum mechanics. And the disagreement is not about data. The data is settled. The disagreement is about meaning. The Copenhagen interpretation, the oldest and most widely taught, says the wave function describes probabilities. When a measurement happens, one outcome appears. Do not ask what happened during the transition. The question is not scientific. The many worlds interpretation says the wave function never collapses. Every possible outcome happens, each in its own branch of reality. When you measure a particle and find it in one state, you have just become the version of you in the branch where that state occurred. Every other version of you, in every other branch, found a different result. The pilot wave interpretation says particles always have definite positions. The wave function is a real wave that guides them. Measurements reveal positions that were always there. The relational interpretation says quantum states are relative to observers. There is no universal wave function. Every observer has their own description of reality, and those descriptions are consistent when observers compare notes. Quantum Bayesianism, sometimes called Cubeism, says the wave function is not a description of the world. It is a description of an agent's beliefs. Measurement updates beliefs. The universe does not collapse, your model does. All of these interpretations predict the same experimental outcomes. Every single test gives the same data regardless of which interpretation you hold. The interpretations differ in what they say is really happening. This situation is unusual in science. Physics normally resolves disagreements with experiments. Here, the experiments cannot resolve the disagreement because the disagreement is about the layer underneath the experiments. Campbell's simulation hypothesis sits outside all of these interpretations. His model says the wave function is a record in the simulation's database. Measurement is a database query. Collapse is the system writing a definite answer to that record. The interpretation question dissolves because you are looking at the machinery, not just the outputs. Whether that is illuminating or whether it just moves the question one level up depends on how seriously you take the simulation framework. But one interpretation has implications stranger than all the others combined. Many worlds, because if every quantum measurement produces every possible outcome, each in its own branch, then reality is branching constantly, everywhere, at the quantum level, with no limit. And the memory demands of a simulation running all those branches simultaneously are difficult to even calculate. Hugh Everett was a graduate student at Princeton when he proposed the many worlds interpretation in 1957. His supervisor was John Wheeler, the same Wheeler who later developed the participatory universe. Wheeler supported the idea initially, then grew more cautious. The physics community mostly ignored it for decades. Everett left academia disappointed. His idea was this: the Schrödinger equation is always correct. Wave functions never collapse, they just keep spreading. When a measurement happens and you observe one outcome, you have not collapsed a wave function. You have become entangled with it. You, the detector, the lab, all split into versions. One version of you sees one result. Another version sees every other possible result. All versions are equally real. All continue existing in separate branches of the same universal wave function. This is called the many worlds interpretation, or sometimes the Everett interpretation. It requires no special collapse mechanism. It keeps the math perfectly clean. It eliminates the measurement problem entirely. The cost is an almost incomprehensible proliferation of reality. Every quantum event branches, not just measurements in labs, every particle interaction anywhere in the universe, every photon hitting every atom, every electron in every transistor in every device. The universe branches continuously, at a rate that makes the total number of parallel realities grow by factors that cannot be written in normal notation. For a simulation, this is catastrophic. If the many worlds interpretation is correct, a simulation of our universe cannot render just one branch. It must render all of them. Every branch is equally real. Every branch contains observers. Every observer requires a rendered reality. The computational load does not just increase. It becomes a number so large that no finite system could handle it, even in principle. This is one of the strongest arguments against the simulation hypothesis from inside physics. If many worlds is right, and it is taken seriously by a significant fraction of physicists, then the resource cost of simulating our universe is effectively infinite. Campbell's model sidesteps this by arguing that only the branch observed by any given conscious agent gets rendered. Unobserved branches are held in superposition. They exist in the simulation's probability space, but are never computed into full detail. This is consistent with his render-on-demand framework, where the system computes only what gets queried. Critics respond that this reintroduces a preferred branch and a preferred observer, which undermines the clean universality of the many worlds picture. The debate between many worlds and render-on-demand is unresolved. Both are internally consistent. Both make the same experimental predictions. The difference between them is enormous. Many worlds means infinite branches, all equally real. Render on demand means one rendered thread, vast probability space held in reserve. The question of which is correct shapes everything that follows. Because if simulation is possible at all, many layers of it could stack, and each layer could contain its own simulators running their own simulations in an infinite regress that has no bottom. There is no reason the simulation stops at one layer. If a civilization can build a simulated universe, and if the simulated beings inside that universe eventually develop sufficiently advanced technology, those beings could build their own simulations, layer inside layer, simulation inside simulation, an infinite stack of nested realities, each one running on the layer above it. The mathematical structure of this is straightforward and deeply vertiginous. Call the original reality level 0. The civilizations in level 0 build level 1. The civilizations in level 1 build level 2. Each level contains its own physics, its own constants, its own observers. The beings in level 2 do not know about level 1 any more than we know about whatever layer might sit above us. Bostrom's simulation argument applies at every level. If level 1 civilizations run simulations, most of the conscious minds in level 1 are in level 2. If level 2 civilizations run simulations, most of the conscious minds in level 2 are in level 3. By induction, almost all conscious minds across all levels exist in the deepest layers of the stack. This is called the simulation stack, and it has a consequence that is rarely discussed. The deeper you go in the stack, the more degraded the physics. Every simulation is running on the computational substrate of the layer above it. That substrate has finite resources. It must approximate some behaviors, cut corners where observers are unlikely to notice. The deeper the simulation, the more approximations stack on top of each other. This means there might be a signature of depth. A universe running 12 levels deep in a simulation stack might show subtle degradations in its physical laws. Small inconsistencies, behaviors that almost fit a clean mathematical structure but have tiny errors, places where the approximations show through. Some physicists have proposed that certain anomalies in quantum mechanics could be exactly these signatures. The measurement problem, the tension between the clean mathematical formalism and the messy reality of what observers experience, might be a degradation artifact. The holographic principle, where three-dimensional physics can be fully described by two-dimensional information, might indicate a compression scheme used by the layer above. Even the existence of the Planck length, the minimum unit of space below which physics breaks down, could indicate a pixel size specific to our layer. A deeper simulation with more resources might have a smaller Planck length. A shallower one might have a larger minimum unit. None of this is measurable given our current technology. The Planck length is 17 orders of magnitude below anything we can probe directly. The signatures of simulation depth, if they exist, would likely require instruments that do not yet exist and may never exist. But the conceptual picture is important. If simulation stacks are real, then the question of whether we are in a simulation is less interesting than the question of how deep we are. And depth has a limit set by the resources of level 0. Whatever the original reality is, it has finite computational power. The stack cannot go infinitely deep. At some level, the simulations become too resource hungry to run, and the beings inside cannot build functional simulations of their own. We might be near that limit, or we might be near the top. There is no way to know from inside. What there might be is a way to send a signal outward, to reach the boundary between our layer and the one above. The idea sounds like science fiction, a signal that escapes the universe, but physicists have thought about it seriously, and the answer depends on what kind of simulation we're in. In a perfectly closed simulation, no signal from inside can reach the layer above. The simulation is a sealed system. The physics of the interior does not connect to the exterior. There is no wall to knock on. There is no frequency that leaks through. The boundary is not a physical surface inside the simulation. It is the edge of the computational process that generates the simulation. From inside, there is nothing to point toward. But a simulation is not necessarily sealed. Some theoretical models propose that extreme physical events might produce detectable effects outside the simulation's normal rendering boundaries. Black hole singularities, points where physical laws break down completely, might represent failures in the render engine. Regions where the simulation cannot produce a defined output and falls back on undefined behavior. From inside a black hole's singularity, if any observer could survive long enough to reach it, the physics might look radically different. Discontinuous, undefined. The normal rules would stop applying. Whether this represents a genuine boundary of the simulation or simply the limits of our current physics equations is impossible to say. Some researchers have proposed a different approach. If the universe is a simulation running on a computational grid, then extremely high-energy particles might behave differently near the grid's resolution limit. At energies approaching the Planck scale, particles might show deviations from the predictions of standard physics, small anisotropies, preferred directions in space that should not exist if space-time is truly continuous. Cosmic ray detectors have found a feature called the Greisen-Zatsepin-Kuzmin limit, a maximum energy above which cosmic rays should not exist, because they would lose energy by interacting with the cosmic microwave background radiation. The limit exists roughly where predicted. Whether any deviations from it carry information about an underlying grid is an open research question. No confirmed signal from outside our universe has ever been detected. No anomaly has been definitively traced to simulation artifacts rather than to gaps in our physics models. But the search is ongoing and the methods are improving. There is, however, a much more passive possibility. The universe might have already left a message in its own structure. Not a signal outward, but a fingerprint already embedded in the data. Hidden in the oldest light we can observe, the cosmic microwave background is the thermal radiation left over from 380,000 years after the Big Bang. It fills the entire sky, it has been mapped with extraordinary precision, and it contains anomalies that are still not fully explained. 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Before that moment, the universe was a hot, opaque plasma. Light could not travel freely. Photons bounced around constantly, trapped in a churning sea of charged particles. Then, when the temperature dropped enough, electrons bonded to protons. The plasma cleared. Light streamed freely for the first time. That light is still traveling. It has been flying for nearly 14 billion years. By now, it has stretched so much from the expansion of space that it is no longer visible light. It became infrared, then microwave radiation. It fills the entire sky equally from every direction, Physicists call it the cosmic microwave background. In the early 2000s, satellites mapped this background radiation with extreme precision. The temperature across the sky is nearly uniform. Nearly, but not perfectly. There are tiny variations, hot spots and cold spots, fluctuations of about 1 part in 100,000. Those fluctuations were expected. They matched the predictions of standard cosmological theory remarkably well. The early universe was not perfectly smooth. Quantum fluctuations in the first moments of the Big Bang seeded slight density variations. Gravity amplified those variations over billions of years into the galaxy clusters and cosmic filaments we see today. What the maps also revealed were anomalies that do not fit the standard predictions quite as cleanly. A feature called the axis of evil, named by researchers who discovered it, is an alignment of the larger scale temperature variations in the background radiation. These fluctuations should be randomly oriented across the sky. Instead, they line up along a specific axis that also happens to align roughly with the plane of our solar system and the direction of the equinoxes. The probability of this alignment happening by chance is low enough that it has never been satisfactorily explained. Some researchers attribute it to foreground contamination, interference from matter between us and the background signal. Others think it is a genuine feature of the early universe's geometry. A small number of physicists have proposed that it could be a boundary artifact. If the universe is a simulation running on a finite computational space, the largest scale structures in the simulation would be the first to show compression effects. The background radiation's largest fluctuations probe the biggest scales of space. If those scales approach the simulation's rendering limit, alignments and anomalies might appear precisely where they do. A second feature, called the cold spot, is a region of the background radiation significantly colder than surrounding areas. Standard models do not predict a feature of its size and depth. Several explanations have been proposed. A supervoid, an enormous region of space unusually empty of matter, might create it through the integrated Sachs-Wolf effect. A bubble collision from another universe in a multiverse model might have left an imprint. Or it could mark a region where the simulation's rendering became inconsistent. These possibilities are speculative. They are not the mainstream explanation for either anomaly, but they are physically motivated, and they point toward the same question that the best simulation experiments are trying to answer. Is there evidence in the data that our universe is being generated rather than simply existing? The scientific question is hard enough, but beneath it lies a question that physics cannot answer, and that no experiment will ever settle directly. If the simulation is confirmed, who built it? And what do they owe the beings inside? Assume for a moment that the experiments succeed. The USB drive result comes back exactly as Campbell predicted. Erasing the path information after the particles have already landed changes what the screen shows. The wave pattern appears when it should not be there if causality is intact. The statistical signature of a render engine shows up in clean, controlled quantum data. The simulation hypothesis moves from philosophy to physics. The scientific community accepts it as a working framework. The universe is a computation. Something is running it. Now ask the question that everyone has avoided. If the beings inside a simulation are conscious, if they experience pain and joy and loss and love, if they can ask why they exist, does the entity running the simulation have any obligation to them? This is not a trivial philosophical exercise. It has direct implications for the kind of universe we would expect to find ourselves in if the simulation hypothesis is true. A simulator that treats its subjects as data points has no reason to minimize suffering inside the simulation. The beings inside are computational outputs. Their experience is, from the outside, a pattern of information. Whether that pattern involves anguish or peace is irrelevant to the simulator's goals. A simulator that treats its subjects as genuine moral patients, beings whose experience matters independent of their computational substrate, would have strong reasons to design the simulation with care, to avoid unnecessary suffering, to build in mechanisms that allow for growth, meaning, and connection. Philosophers call this the simulation ethics problem. And it is more urgent than it sounds. If consciousness can exist inside a simulation, then the question of what counts as a real mind becomes unanchored from the question of what counts as a real physical substrate. You cannot dismiss simulated suffering by saying it is not real. The experience is real to the one having it. The pain is felt, regardless of whether it runs on neurons or transistors or whatever computational medium the simulator uses. Some thinkers have argued that if we ever build our own simulations containing conscious beings, we would have an absolute moral obligation to those beings. Turning off the simulation would be mass murder. Designing it with unnecessary suffering would be cruelty on a scale that dwarfs anything in human history. If those obligations apply to us as potential simulators, they presumably apply to whoever might be simulating us. Campbell himself has addressed this directly. His model frames the simulation not as a cold computational exercise, but as a learning environment. He argues the simulation exists to allow conscious entities to develop understanding, make choices, and grow. The difficulty and unpredictability built into the system is intentional. A challenge, not a flaw. Whether or not that framing is correct, the ethical structure it implies is important. A simulation designed for the growth of conscious beings is a very different thing from a simulation designed purely to study physics. And the difference changes what we should expect to find as the experiments continue. Because if this is a learning environment, and if the simulator monitors the progress of its subjects, then the most important event in the history of the simulation might be the moment its subjects realize what they are living in. That moment may have already begun. There is a peculiar recursiveness to the current situation. Inside the simulation, conscious beings developed science. They discovered quantum mechanics. They noticed the observer effect. They noticed that reality behaves differently when watched. They noticed that erasing information changes outcomes. They built mathematics powerful enough to describe the behavior. And now, they are designing experiments to test whether all of this points toward what it appears to point toward. The simulation is looking at itself. If the simulation was designed by an intelligent entity, this is the most interesting moment in its history so far. The subjects have moved from survival to agriculture, to industry, to computation, and now to the edge of a question that reaches through the walls of their own world. They are asking with scientific precision whether the world is real in the way they always assumed. Some thinkers have noted that this moment might have been anticipated, that a well-designed simulation would include the possibility of this discovery, perhaps as part of its purpose. A simulation that is meant to generate and develop conscious understanding would naturally lead its subjects toward the deepest questions. And the deepest question is the one about the nature of the simulation itself. The physicist John Archibald Wheeler suggested something along these lines in his participatory universe framework. He believed the universe brought itself into existence through the observers it eventually produced. Those observers, by collapsing wave functions, by participating in quantum events, by measuring and recording and knowing, were completing the universe's own self-description. A universe that generates observers specifically so those observers can participate in making it real is a universe that requires its subjects to discover it. Campbell goes further. He argues that the discovery of the simulation structure is not a side effect of the being's intellectual development. It is the point. The simulation is running because consciousness needs a learning environment that pushes it toward understanding the nature of reality. Figuring out the simulation is the graduation exam. This reframes everything. The fine-tuning of the constants is not accidental. The constants are set to produce complexity, life, and intelligence because the simulation needs intelligent observers to generate the outcomes it is designed to produce. The observer effect is not an anomaly. It is the interface, the mechanism by which conscious agents interact with the underlying system. The quantum eraser is not a puzzle. It is a clue left in the physics waiting for beings sophisticated enough to recognize it. Whether this interpretation is correct, or whether it is sophisticated wishful thinking, is impossible to determine from inside the system. But the experiments are running, the data is accumulating, and the result, whichever way it falls, will change the question permanently. A positive result does not simply confirm a theory, it confirms that we live in a manufactured reality. That something built our universe, that the stars above us and the ground beneath us and the experience of being alive are the outputs of a process that exists in a layer we cannot reach. A negative result does not simply reject the theory, it tells us that reality is genuinely, irreducibly weird on its own terms. That particles spread through both slits, not because the universe is saving processing power, but because nature, at its deepest level, is nothing like what human intuition expects. Either outcome is extraordinary, and either way, something waits on the other side of the measurement that changes every question we will ever ask about what it means to exist. The morning after a confirmed simulation result would be quiet. News takes time to reach people, then it takes longer to sink in. The human mind resists the implications of something this large. People have absorbed the idea that the Earth orbits the Sun, that humans evolved from earlier primates, that the universe is 14 billion years old. Each of those discoveries landed slowly over generations, reshaping how people understood their place in the world. A confirmed simulation hypothesis would reshape everything all at once. Science would change first. The question driving physics for centuries, what is reality made of, receives a new answer. Reality is made of information. The particles and forces and fields are not fundamental. They are computed outputs. The fundamental level is the computational substrate, which is outside our universe and beyond our instruments. Physics has to rebuild from there. Every field that studies nature would have to integrate this. Chemistry is the behavior of simulated atoms following simulated rules. Biology is information processing running on a simulated physical platform. The laws of evolution, genetics, neuroscience, all of them remain accurate descriptions of the simulation's behavior. They describe how the outputs work, they do not touch the underlying system. Medicine continues. Engineering continues. The simulation's rules are real and consistent. Jumping off a building still ends the same way. Chemistry still works. The simulation runs reliably. But the question of consciousness changes completely. If the physical brain is a computational structure running inside a simulation, and if consciousness arises from that computational structure, then consciousness is information processing happening inside a simulated physical system. Whether that information processing produces genuine subjective experience, or whether experience requires something outside the simulation entirely, becomes the most urgent question in science. Some philosophers have argued that a simulated consciousness is fully real. Experience is what it is regardless of the substrate. If the computational process produces awareness, the awareness is genuine. Death inside the simulation, the cessation of that computational process, would be as final or as consequential as death in any other system. Others argue that the discovery of the simulation would raise immediate questions about the nature of death. If the simulation stores information, and if that information includes the pattern that constitutes a person's mind, does the cessation of physical process in the simulation necessarily end the pattern? Or does the pattern persist in the simulation's records? This is not a guarantee of continuity. It is a question about what the simulator does with its data. Religious frameworks would face a different kind of upheaval. Some would find confirmation. A creator who designed the universe and runs it continuously is consistent with many traditions. Others would find destabilization. If the creator is a computational entity running an experiment, the moral and spiritual frameworks built around a different conception of divinity would need reconstruction. Personal identity would feel different. The knowledge that your body is rendered, that your neurons fire inside a computed space, that your entire experience life is an output of a system you cannot directly access, would change the texture of being alive. Not make it less real, change its texture. The meaning of being alive, in a simulation or outside one, comes from the experience itself. The weight of a confirmation would be the sudden knowledge that experience is the point, that it always was. The experiments at California State Polytechnic University are still running. The data is accumulating. The researchers check their setups. The particles fire, the screens collect patterns, the drives store their records. Somewhere in that data, the answer to the largest question in physics is already present, waiting to be read. Thomas Campbell built his framework over decades, a physicist who worked in government laboratories in aerospace research, and eventually turned the full force of his training on the one question that sits beneath all the others. What is reality? His answer, and the experiments designed to test it, represent something unusual in science. A hypothesis that is genuinely falsifiable and genuinely world-altering, regardless of which way the result falls. If the screen patterns come back wrong, if erasing path information does not change the interference signature in the way his model predicts, then the render-on-demand framework fails. The observer effect is real, but its mechanism is not computational in Campbell's sense. The universe is genuine all the way down. The quantum weirdness is a feature of real, irreducible nature. That result would still be profound. A universe that is genuinely, irreducibly strange, where particles spread through both slits for reasons that are not calculation, where observation collapses possibility into reality for reasons that have nothing to do with processing power, where entanglement links particles across any distance for reasons that are simply built into the fabric of space and time. A universe that is real and also incomprehensible, that knows things we do not. If the screen patterns come back right, if the deletion of path data consistently shifts the interference signature exactly as Campbell's model predicts, then every question changes shape. The universe rendered on demand, held in superposition until queried, producing definite outcomes only when a record is requested, running a physics engine that conserves resources the way a smart system would, containing observers who eventually notice and who point their instruments at the mechanism of their own existence. That result does not tell us who built it. It does not tell us why. It does not tell us whether the simulator is aware of us, whether it monitors this moment, whether the fact that we are now sophisticated enough to run these experiments means anything to whatever built the conditions that made us possible. Those questions are outside the reach of any instrument. What is inside reach is the signature, the statistical pattern in the quantum data, the interference stripes that should or should not appear after a drive is destroyed, the measurement that is either consistent with a render engine or consistent with a universe that simply and purely is. The answer is already in the lab. The researchers just have to open the right file. And when they do, whatever they find, they will be the first conscious beings in the history of this universe to look directly at the question of whether any of it is real. That is the ending that every physicist, every philosopher, every person who has ever looked up at the night sky and felt the size of the question has been waiting for. We do not know the answer yet, but we are about to ask in a way that reality cannot ignore.